This is problem 1 on practice exam 4 of chapter 1 in the book Problem Solving with Differential and Integral Calculus. It takes four times as much paint to paint a sphere of radius r than it does to paint a circle of radius r. The normal equation for the surface area of a sphere is 4 pi r squared. The equation for the area of a circle is just pi r squared. Part A asks for the difference equation that relates the difference in the surface areas of two spheres to the difference in the radii, delta r. Let's focus on that one first. So we have the normal equation. We'll call that A1, 4 pi r squared. We have a different gumball with a radius of r plus delta r. It has an area which we'll call A2. The difference between those two areas is A2 minus A1. So we just subtract them. We FOIL out the r plus delta r squared, and we get this. We can distribute the 4 pi in there. We have a 4 pi r squared here, a minus 4 pi r squared there, the surface area of the smaller sphere. Those cancel out, and we're left with 8 pi r delta r plus 4 pi delta r squared. This is the difference in surface area between a sphere of radius r and a sphere of radius r plus delta r. And it's exact. On to part B. There's a gumball manufacturing company. They want to know the difference in surface area between a gumball with a radius of 5 millimeters and a gumball with a radius of 15 millimeters. So we can use the difference equation. There it is. We just derived it. R is 5 millimeters and delta R is 10 millimeters to get up to 15. The change is 15. The difference is 15. So we just plug in 5 millimeters for R, 10 millimeters for delta R, and we punch the numbers on the calculator, and we get 2513 square millimeters for the difference in surface area. We can check it. It's easy to check it because we have the normal equation. So the surface area of a gumball with a radius of 5 millimeters is 4 pi times 5 millimeters squared. That's about 314 square millimeters. Surface area of a gumball with a radius of 15 millimeters. All we do is plug in 15 millimeters to the normal equation. We get 2827. We subtract these two to get the difference, and it's 2513, as we expected. 2513 square millimeters. We got the same thing with the difference equation. It's right here. 2513 square millimeters. Use the normal equation twice, subtract the results, 2513 square millimeters. Part C says compare the linear term and the nonlinear term. Can the nonlinear term be ignored in this case? You probably already know the answer to that. So the difference equation is 8 pi r delta r plus 4 pi delta r squared. The first term is a linear term. It has delta r in it. The second term is the nonlinear term because it has delta r raised to a power that's not 1. In this case, it is 2. It's delta r squared. So the linear term had a magnitude of 1257, and the nonlinear term had a magnitude of 1257. So you can't throw away the nonlinear term. You're going too far away from r. The tangent line isn't close to the curved line when you go that far away. So we started at 5 millimeters. We didn't go to 4.98. We didn't go to 5.03. We went all the way to 15. That's too far to go. And we shouldn't expect the nonlinear term to be really small. And we can look at it on a graph. All right? So starting at 5, there's the tangent line. If you're close to 5, the tangent line follows the actual line. But once you go way over here, the tangent line is way off. The actual delta A is way up here. The delta A from the linear term is down here. So delta A is 8 pi r delta r plus 4 pi delta r squared. The slope of the tangent line at the point r, 5 millimeters, we can ignore this one. We can ignore the squared term. What about the linear and nonlinear contributions to delta A? Can you find them on the graph? So the slope of the tangent line is the linear portion of delta A because it's a straight line. So we could ignore this term because we're really close to the point. We're getting the slope at the point. So we ignore this term and we just put the delta R in the bottom. We got delta A over delta R. Delta A is the rise. Delta R is the run. And the slope is 8 pi R. What about the linear and nonlinear terms? Can you find them on the graph? There they are. Linear term starts at 5, goes up to the tangent line. That's the nonlinear term, and as we saw, those contributions were the same, and they look about the same. If we're in close here, the linear term dominates. So if the line is curved and the change in the variable is not small, you're getting too far away from the line. We should not expect the linear contribution alone to be a good approximation to the change. It should make sense to you. I understand it now. I see how this works. That's the goal. You shouldn't be surprised that when you start at 5 and you have a delta R of 10, that you're going to get a good answer with just the linear term. Thanks for watching.